beginning, nearly 14 billion years ago, all the space and all the matter and all the energy of the known universe was contained in a volume less than 1/trillionth the size of the period that ends this sentence. Conditions were so hot, the basic forces of nature that collectively describe the universe were unified. Though still unknown how it came into existence, this sub-pinpoint sized cosmos could only expand rapidly in what today we call the Big Bang. Einstein's general theory of relativity, put forth in 1916, gives us our modern understanding of gravity, in which the presence of matter and energy curves the fabric of space and time surrounding it. In the 1920s, quantum mechanics would be discovered, providing our modern account of all that is small: molecules, atoms, and subatomic particles. But these two understandings of nature are formally incompatible with one another, which set physicists off on a race to blend the theory of the small with the theory of the large into a single coherent theory of quantum gravity. Although we haven't yet reached the finish line, we know exactly where the high hurdles are. One of them is during the Planck era of the early universe. That's the interval of time from t equals 0 up to t equals 10 to the minus 43 seconds. 1/10,000,000,000,000,000,000 trillionths of a second after the beginning. And before the universe grew to 10 to the minus 35 meters, 100 billion trillion trillionths of a meter across. The German physicist Max Planck, after whom these unimaginably small quantities are named, introduced the idea of quantized energy in 1900 and is generally credited as the father of quantum mechanics. The clash between gravity and quantum mechanics poses no practical problem for the contemporary universe. Astrophysicists apply the tenets and tools of general relativity and quantum mechanics to very different classes of problems. But in the beginning, during the Planck era, the large was small, and we suspect there must have been a kind of shotgun wedding between the two. Alas, the vows exchanged during that ceremony continue to elude us, and so no known laws of physics describe with any confidence the behavior of the universe over that time. We nonetheless expect that by the end of the Planck era, gravity wriggled loose from the other still unified forces of nature, achieving an independent identity nicely described by our current theories. As the universe aged through 10 to the minus 35 seconds, it continued to expand, diluting all concentrations of energy, and what remained of the unified forces split into the electroweak and the strong nuclear forces. Later still, the electroweak force split into the electromagnetic and the weak nuclear forces, laying bare the four distinct forces we have come to know and love, with the weak force controlling radioactive decay, the strong force binding the atomic nucleus, the electromagnetic force binding molecules, and gravity binding bulk matter. A trillionth of a second has passed since the beginning. All the while, the interplay of matter in the form of subatomic particles and energy in the form of photons, massless vessels of light energy that are as much waves as they are particles, was incessant. The universe was hot enough for these photons to spontaneously convert their energy into matter-antimatter particle pairs, which immediately thereafter annihilate, returning their energy back to photons. Yes, antimatter is real, and we discovered it, not science fiction writers. These transmogrifications are entirely prescribed by Einstein's most famous equation, E equals mc squared, which is a two-way recipe for how much matter your energy is worth and how much energy your matter is worth. The c squared is the speed of light squared, a huge number which, when multiplied by the mass, reminds us how much energy you actually get in this exercise. Shortly before, during, and after the strong and electroweak forces parted company, the universe was a seething soup of quarks, leptons, and their antimatter siblings, along with bosons, the particles that enable their interactions. None of these particle families is thought to be divisible into anything smaller or more basic, though each comes in several varieties. The ordinary photon is a member of the boson family. The leptons most familiar to the non-physicist are the electron and perhaps the neutrino. The most familiar quarks are, well, there are no familiar quarks. Each of their 6 subspecies has been assigned an abstract name that serves no real philological, philosophical, or pedagogical purpose, except to distinguish it from others. Up and down, strange and charmed, and top and bottom. Bosons, by the way, are named for the Indian scientist Satyendra Nath Bose. The word lepton derives from the Greek leptos, meaning light or small. Quark, however, has a literary and far more imaginative origin. The physicist Murray Gell-Mann, who in 1964 proposed the existence of quarks as the internal constituents of neutrons and protons, and who, at the time, thought the quark family had only 3 members, drew the name from a characteristically elusive line in James Joyce's Finnegan's Wake. 3 quarks for Muster Mark. One thing quarks do have going for them: all their names are simple. Something chemists, biologists, and especially geologists seem incapable of achieving when naming their own stuff. Quarks are quirky beasts. Unlike protons, each with an electric charge of +1, and electrons with a charge of -1, quarks have fractional charges that come in thirds. And you'll never catch a quark all by itself. It will always be clutching other quarks nearby. In fact, the force that keeps 2 or more of them together actually grows stronger the more you separate them, as if they were attached by some sort of subnuclear rubber band. Separate the quarks enough, the rubber band snaps, and the stored energy summons E = mc² to create a new quark at each end, leaving you back where you started. During the quark-lepton era, the universe was dense enough for the average separation between unattached quarks to rival the separation between attached quarks. Under those conditions, allegiance between adjacent quarks could not be unambiguously established, and they moved freely among themselves, in spite of being collectively bound to one another. The discovery of this state of matter, a kind of quark cauldron, was reported for the first time in 2002 by a team of physicists at the Brookhaven National Laboratories, Long Island, New York. Strong theoretical evidence suggests that an episode in the very early universe, perhaps during one of the force splits, endowed the universe with a remarkable asymmetry, in which particles of matter barely outnumbered particles of antimatter, by about 1,000,000,001 to 1,000,000,000. That small difference in population would hardly get noticed by anybody amid the continuous creation, annihilation, and recreation of quarks and antiquarks, electrons and anti-electrons, better known as positrons, and neutrinos and antineutrinos. The odd man out had oodles of opportunity to find somebody to annihilate with, and so did everybody else. But not for much longer. As the cosmos continued to expand and cool, growing larger than the size of our solar system, the temperature dropped rapidly, below 1,000,000,000,000 degrees Kelvin. A millionth of a second has passed since the beginning.